Today we are going to talk about one of the most useful things in machine learning. It is called linear regression. It is perhaps the simplest thing that you will ever learn in any machine learning course. And I bet that in this room, many of you have already learned linear regression more than once. Okay? So what I would want to do today is not to make you feel boring again by just showing you some equations that I bet you have seen before, but I will want to bring up some perspective from the linear algebra point of view of what this linear regression is actually doing and how this linear regression is going to be positioned in a learning algorithm, that framework. Okay, so this is a rough outline of the 5 lectures that we are going to go through in the first part of the course. In these 5 lectures, we will study linear regression, okay, a very simple method that can go through all these 4 blocks in the diagram that I'm showing here. What are the 5 blocks? Well, you have a data coming in, and so you want to extract the features. Then you want to put a prediction model, and then you want to measure the loss. And then you want to apply it to an optimization algorithm, and then find a solution, then feedback, and then update your model parameters. Okay, so this is a very closed loop of a machine learning algorithm. So what is lecture 1? The lecture 1 on linear regression will focus on the prediction model. It is an extremely simple model using just a line. And we want to show that this line is very powerful, that it can solve a lot of great engineering problems. So if you understand how linear regression works, I promise that you will solve a big number of problems that you're encountering in your own projects. The outline of today's lecture will be as follows. It is lecture 1 on linear regression, some basic analytic tools. We have 2 parts of this lecture. We want to talk about the basic notations of linear regression, and then we want to define the thing, what do I mean by loss function in a regression setting. And then I want to comment on how do we solve the regression problem. So that's part 1, some basics about linear regression. Then I want to jump into a little bit more abstract setting called the geometry of linear regression. This geometry will play a very, very powerful role in the later part of the course when you try to understand what is the meaning of a feature. What do I mean by error? What do I mean by norm? Those notions will play a big role in a typical machine learning problem. So I want to spend some time talking about the geometry. The geometry will be abstract, and I hope you can really spend the time to understand the geometry behind the linear regression case. Make sure you get the point, and then so that when you solve the problem, you know what you are doing. Okay, so just some very simple introduction of the notations. I am going to use the following set of symbols. If I'm going to describe a scalar, they will be small letters A, B, C, and then they're all in the real space R. If they're vectors, I will put the bold letters. And if they're matrices, they will become capital letters A, B, and C. Now, I want to differentiate the notations between the columns and rows of that matrix A. The columns then denoted by A1 through AD, where D is the dimensionality of that matrix, and that is counting how many number of columns are there, or I can call that how many feature vectors are there in my data set. The rows of the A matrix, they are the data samples. So think about it in the following way. I go out and I do a survey, and I get the scores of the incoming students. So that could be the GPA, that could be your GRE scores, that could be your scores that your professors give you in the recommendation letters. Right? So these are different features. So I approach student 1. The student 1 will have all these features stacked together. So the first entry will be your GPA, second entry will be GRE score, and so on. These will be one row, okay? So you are a student, you are a data sample point, and so you have one row of all these features stacked in one row. This is x1 through xn, okay? So that's one row. And then the columns will be all the students and then their GRE scores. So that column represents the GRE score column. These two are two different perspectives of that A matrix. Do you want to look at the prediction as a function of the features, or do you want to look at the prediction as a function of the person? Okay, so one is the column space perspective, the other one is the row space perspective. There are two different perspectives, and they're playing different roles in this machine learning algorithm, and they have different applications. Okay? They also have different geometries that we want to spend time and understand. Okay, and so if I have identity matrix, it will be I, all one vector it will be 1, all 0 vector will be 0, and then a standard basis, it will be EI. It means that you have a column vector, only the ith element is 1, otherwise it will be 0. Okay, so that's the basic notation. What is linear regression? The linear regression is a very simple problem. I give you a set of data points, and then I ask you to find a line that would be best fit to all these data points. It's as simple as this problem, okay? Now you can see that, okay, this problem is easy. I put all the data points into my Excel spreadsheet. I click a button, I get a result. But let me ask you, what does Excel do behind that button? Well, it's actually doing some kind of curve fitting. And behind this curve fitting, you're actually solving a linear system equations. And by solving this linear system equation, there's a loss function associated with that. And there is a method that solves the problem for you. So there are a couple of steps when you're trying to solve this line fitting question. So I want to put the linear regression into a slightly more abstract way so that we can generalize this concept to other problems. Okay, so this is a very simple problem. It's a toy problem on linear regression, but I want to use the same notation that can be translated to other problems later on in the semester. So what do I have? Well, you have a set of measurements, yn. These are scalar numbers because you have, think about you have all the GRE scores or the GPA numbers, and then you have a number. That would be the predicted value, how the overall score of the student, whether we should admit or not, right? So that will give you one score. That would be yn. N stands for the nth sample. The input would be one row, okay, that, the data point of that student. And then what would be the model? The model is denoted by G subscript theta. This is a model that you pick. In this case, it would be a linear model. I put a theta there because I want to parameterize my model using a parameter theta. So theta could mean what? In the previous plot, it would mean the slope and also the y-intercept. Okay? So these are the trainable parameters. By finding out the theta, you can define the line. The goal here is very simple. You want to find the best theta so that all the yns will fit well with the prediction, which is g applied to xn. Is that clear? All right. Now, linear regression is a special type of regressions. And in this linear regression setting, you are going to restrict g to a linear function. And by linear function, I really mean that you have the theta vector, you do an inner product with the x. Okay, so that will define a line. And what are the x? Well, x will have the dimensionality of d because you have d features, and that's why you have d elements. The parameters, you also have d because now you're taking the inner product between theta and x, and so the dimensionality has to match. This is equivalent to the equation that I'm showing at the bottom, which is the sum of the theta i's and xi's. Now, once we have defined the notation, let's also try to define the loss function, because in any machine learning algorithm, you want to settle the loss function, and then you want to minimize the loss function. So what is the loss function here? In the regression case, we are going to define a loss called the L. The L will take two inputs. One is your predicted value, which is the G, applied to your input data X. And then you have the value Y. Y is your actual measurement. you put the loss function, and the loss function will calculate the difference between the two, and you sum over all the possible samples in your training set, and sum them all, you call that as the loss. And in particular, if I choose the square loss, which means that I put the square difference between your prediction and also your measurement, that will give you the square loss function. You sum everyone up. That is the loss function that we use in linear regression setting. Now you ask, can I use another form of loss? Yes, you can. But why do we choose square? It's because square is differentiable. You like things to be differentiable so that you can take derivatives, set it to 0, and then get an analytic form. You can use the one norm, which just put the absolute value as your loss function, as I'm showing you in the second point here. You can do that, but then you need to pay the price of solving a little bit more difficult optimization problem. Okay? In this problem, you may not even have a closed form if the loss function is more complicated. The goal of the regression is to find a theta such that your loss function is minimized. Okay? And so once you have this minimized loss function, you will get a minimizer, and this is called the theta hat. And once you put this theta hat into your model, you can put in a new testing data point, I call it x new. You put it into your model, and then this model will return you the predicted value. Okay? If it matches well, you're happy. If it doesn't match, you go back and you debug. Okay? So that's the general framework of what is the model that you're choosing here? It will be a linear model. What is loss function? Square loss function. What is problem? It's a minimization problem. Okay? So that covers the generic pipeline of machine learning. Any machine learning problem is framed in this way. Okay? You have your algorithm that will solve a loss function in a similar manner. Okay, so now let's just jump a little bit into the equations. So let's restrict ourselves to a line. Then what do we have? Well, then you have this equation at the first point. You have G equals to X transpose theta. Then what would be the loss function? Well, since I choose a square loss function, I can write them as the summation of the square terms between all the differences. And then I can also rewrite that summation as a two-norm square. That's just coming from the linear algebra. The two stroke here means the norm, the vector norm of the vector, and that literally means that you take the difference between the two elements and then take the square and then sum them up. That will be the norm. Okay. The A matrix here is just the A matrix that we saw. It will be all the rows, and then the theta will be a vector of the feature values. We call these thetas as the regression coefficients, okay? And we want to analyze these regression coefficients. Okay, so what is the minimization problem here? If you solve this minimization problem, that means you want to take the derivative of this loss function, set it to 0, and then do some linear algebra, and then get the inverse, then you can get a solution. So in this theorem, it shows you that if you're looking at this minimization problem, then there is a minimizer, and this minimizer is given by this A transpose A inverse A transpose Y. Now, I'm making an assumption here that your A transpose A is invertible. Okay, I will comment on this when we go to the geometry. When A is not invertible, then what do you do? So assuming that A is invertible, then this is the solution. And how do we get that? Well, I'm showing you the derivation at the bottom. Okay? Literally just taking the gradient of that loss function. If you are not familiar with the gradient, you're welcome to take a look at the linear algebra tutorial. At the last section of that tutorial, you will find a few examples on taking gradients of vectors. So that would be very useful. And in this course, we will normally deal with loss functions with square terms. So make sure that you understand how to take the gradient of a square function. Okay, so this is the solution. The solution is given by this form, assuming that A transpose is invertible. So let me give you some quick examples. Okay. I can use the previous model to solve the line fitting problem. Okay, so I just have a bunch of data points to find a straight line to go through it. That's very simple. Okay, or you can try to fit in a second order polynomial, In the second order polynomial, you have a quadratic equation. So you have axn squared, bxn, and then c. You can put all these xn squared and then xn, and also the last one will be 1, okay, into the matrix. You set up your yn's, you set up your thetas, and then you solve this equation. Previous slide, you can look at this equation, it will be the same equation. Okay? Clicking a button, and then you get a solution. You can use the same approach to solve an autoregression problem where yn is equal to yn minus 1, meaning that if you are at time n, you look at your previous sample and 2 samples before you. Okay? That would be very useful when you look at stock markets, okay? Or you're trying to look at speech signals, where you're trying to look at samples that came before you. Okay? This is called the autoregression model, and then there are A's and B's in this equation. You want to find out the A's and B's. And so what would be the A matrix? Well, the A matrix would be just the columns of all the Y's with a shifter index so that it will match with the Y vector that you have in your measurement. All right? Okay, so then you can solve for A and B's in this equation using the linear regression approach. You can generalize this linear regression approach to even more complicated problems. This is a typical problem if you take a signal processing course, which is called the Fourier transform or the Fourier series expansion. It says that if I have a set of sinusoidal functions, they are different by the frequency. So you have a nominal frequency omega naught, and then you just take the integer multiples of all these frequencies. You have a set of sinusoids. And we ask, if I give you a function that I'm showing you at the bottom, which is the blue one, and then I give you all the data points, the blue crosses. Okay? Find me the blue curve that comes from a linear combination of all these red curves. Right? So the blue curve has to be a linear combination of the red curves. I tell you that I believe that all these data points would be the certain number times the first red function, and then plus a certain number times the second function, and so on. Okay? So this is called the Fourier series expansion on a function. And you can also solve this problem using the linear regression. Okay? And then now you can extrapolate this idea to other things. You can have a polynomial you can extrapolate. You can have your own defined basis functions you want to interpolate using the linear regression model. You can find out the regression coefficients. Okay? So all these can be applied using just a very simple principle. Okay, any questions so far? Okay, now, if not, let's spend some time into the geometry of this linear regression. Okay, and this is a little bit harder, so I want to spend a little bit more time there. So let's talk about the geometry. Now, there are a couple parts of the geometry. One is the projection, the other one is the minimum norm solution, and then the last one will be the pseudo-inverse perspective of the solution. Okay, so first of all, we want to understand some notion of this linear algebra. I'm going to define a notion called the linear span. Okay, hopefully you have taken the linear algebra course, you know what I'm talking about. If not, it's also not too difficult to understand. Suppose you have a set of vectors, A1 through AD, so they are the feature vectors. Okay, so in this A matrix, they are the feature vectors. I'm going to form a linear combination of all these feature vectors. All right, then I will define a set called the span of A1 through AD. That would be the set that contains all the linear combinations of all these column vectors. Now you ask, well, why are you interested in looking at these? Well, think about going back a little bit, okay, to the regression problem, where you have all these columns. They are the GRE scores, they are the GPA scores, and so on. And you want to find a regression coefficient. You want to say, I want to put so much emphasis on the GRE, typically not too much in our graduate admission, but you want to put more emphasis on the GPA because it really matters. All right? So you want to look at the linear combination of all these column vectors, and that's why we want to study the span of all these vectors. Then we ask, okay, now you have the span defined. Can you give me an example? Well, it's very simple. If you have R3, okay, you have a three-dimensional vector space. Okay, they're all real numbers. Any independent vectors, these three vectors, they can span the entire R3. Okay, they do not need to be orthogonal. Even they're like this, you are fine. Okay. But the third case is not, because the two vectors that I'm showing you here, they're parallel. One is the opposite of the other. So they do not span the entire R3. They only span R2. Right? So this is the notion of a linear span. And so the geometry of this linear regression is as following. You imagine that there is a space. Okay? It's a flat space. And in this space, it contains all the A vectors you have. Okay, and in this space, what does the space contain? It will contain all the linear combinations of all the basis vectors I have. All right. So think about in this picture I'm showing you here. So you have okay. I want to draw something here. Okay. All right. So think about what do you have? Well, you have a vector A1. You have another A2. So since we only in this diagram, I can only draw 2D. So let me restrict myself to the two vectors. And so now you have these two vectors, A1 and A2. And you can start to ask, okay, what are the possible linear combinations of all these A1 and A2? Well, this one can be a linear combination of the A1 and A2. Just put the right number. This vector can also be a linear combination of A1 and A2. So you can eliminate all the possible vectors. That will give you a plane of vectors that can all be spanned by the vectors A1 and A2. Now you can generalize this idea to more vectors where you have A1 through AD. That now it will be a d-dimensional space. So a linear combination of all these d-dimensional vectors will give you that space. So now I give you a vector y. The y is a observation. And that observation, of course, is not very happy with you. Okay? And so the noisy vector will not live on that space. Okay? So this noisy vector is outside the space. And so you have a point here. That's your y. So what you're trying to do? What you're trying to do is to find the closest point on your plane, okay, such that that y vector can be closest to you. So what do you do? Well, you start to measure the distance between this y and any point on the plane. So let me ask you, what would be the closest guy? Well, would this one be the closest guy? No, this vector will not be the closest guy because it's not perpendicular to the plane. So is this point is not perpendicular to the plane, so it won't be the shortest distance. So which one will be the closest distance? Well, it has to be the one that is perpendicular to your plane. Okay? And linear regression, that magical formula with the A transpose A inverse, that kind of thing, is doing this. Do you see that? Right? So you give me a y vector, and then I will look for the basis vectors you give me, and then I want to find the best linear combination among all these AIs. Find one point. Okay, this point is not necessarily A1 or A2. It would be a linear combination of A1 and A2. What would be the linear combinations? Well, that would be a regression coefficient theta 1 and theta 2. These will be your solution. Okay, so you find this point. This point will be closest to your y, and they live in that span of your vector space. Okay? Have that picture in mind. That explains what linear regression. Nothing more than that. It's just this simple picture. Okay, so I also define a thing called the R of A. This R of A is called the range space of A. It's also the column space of A. It says that it contains all the possible y hat such that y hat is A theta. Okay? In this case, of course, it doesn't live in this RA. Now, RA is really that plane. Okay? All right. So this slide summarizes a few keywords that you can find in a textbook. The first notion is called the error. What is the error? The error is your y subtract from your plane. Okay? So it will be y minus A theta. That's your error. And so if you refer to my drawing, then what is this E? Well, this is your E. E equals to y minus A theta. That is your error. Okay? Now, the error can be big, can be small. Of course, there is one error, which is minimized. And so according to this diagram, we know that the error is minimized when your error vector is perpendicular to your plane. Right? This is called the orthogonality principle, another keyword that you will find in many textbooks. Okay? So this orthogonality principle says that this E, for this E to be minimized, it has to be perpendicular to your plane. So what does it mean? Well, I have a vector E, and then I know that all the vectors in this plane, they are linear combinations of A1, A2, A3, and A4, and so on. So I can do an inner product of this E transpose of your AJ. Okay, let's do an inner product between this E and the AJs. What will happen? It has to be 0, okay, because they're orthogonal. And this has to hold for all the J's. Right? Now, if it has to hold for all the J's, then that means this E transpose of a matrix that contains the A1, A2, dot, 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 A, D, all these column vectors, they have to be 0 if each individual is 0. Do you get that point? Okay. And then now I can rewrite this equation as what? As just A transpose E equals to 0. All right? Okay. So, so what? Well, if you have A transpose E equals to 0, then let me just write down the equation of A transpose E equals to 0. And I know that the E is just y minus A theta equals to 0. Then what do I have? I have A transpose y equals to A transpose A theta. That is the linear regression solution. Okay? So you don't have to take the derivative set it to 0 to get the solution. You can just draw a diagram, draw the plane, draw the line, and then perpendicular, you get the solution. You get the exact same solution as what we used to see using the vector calculus. This equation is called the normal equation, another keyword that you will easily find in a textbook. And then it's just A transpose A theta equals to A transpose Y. Now, if you want to get the predictor value, you just put the A matrix next to your theta hat, then you will get the predictor value. That would be the expression. This is the third point in the slide. And then you can also look at the matrix now. The matrix now contains the inverse. And then on the left, you have an A. On the right, you have A transpose. This is called the projection matrix. What is it? Well, you go back to the previous diagram. What is the y hat? The y hat is this vector. This is your y hat. Why? Because you have projected your y onto the plane, and then that would be the best possible prediction that you can ever have. Okay, so there's a projection matrix. And since it is a projection matrix, you don't need to project it multiple times because, see, once you are on that plane, no matter how many times you project, it will still be on the same plane. So you have the property that you multiply P with P, it's still the P. Okay? And then the error, you can also define it using I minus P on the Y. Okay? Okay, so that is the notion of the normal equation, the projection matrix, and other keywords that you would normally find in a textbook. Okay, so what's next? Let's also spend some time on talking about matrices with different ranks. Okay, so let me. Any questions so far before I move on? Yes. The question is would the A vectors represent the features? Okay, so here the A vectors, they are given by you. Okay, so they are predefined. They're the data matrix, so they are feature vectors. Okay, so A1 would be feature vector 1, A2 would be feature vector 2. So in this linear regression problem, the A's are defined by the user. They are not optimization variables. Okay, so they are the feature vectors. The notion of this, the thetas, okay, so once you solve this problem, you get the thetas. So this theta will be theta 0, theta 1, theta 2, and so on, theta d. They are the regression coefficients. Okay, these are the regression variables. They are the optimization variables. Okay, more questions? Yes.
How do you know if y is possible to be spat by the matrix, whether it lies in the plane or out of plane?
Okay, so the question is whether I know that y is on the plane or not on the plane.
Yeah,
okay, so can we check that whether y is on the plane or not on the plane? You can do it. You can solve this problem. If the error gives you is 0, then you're on the plane, right? And so if I give you a data point, I give you a vector. First, I give you a vector. I want to know, okay, what would be the how does it look like on this diagram? Of course, you don't know because it's high-dimensional vector. You cannot see that. Okay, and so what you would do is that you solve the problem. If it turns out that y can really be expressed as the linear combination of a's, you will get 0 error. Okay, typically you cannot, especially when you have a few columns, but you have many rows. Okay, because then you will not be able to express all the possible y's. It would be a different case as what I'm going to talk about when you have an underdetermined system, which is a fat matrix. You have more columns than rows. Then, in many cases, you can express your y in terms of the columns. Okay, so there are two different situations here. Okay, so since you're asking this question, let's talk about this overdetermined and underdetermined system. So let's first assume that A has a full column rank. So if you look at this matrix, all the columns, they're independent. Now, we have a slide talking about when some of the columns, they are dependent. So that's a more difficult problem. So for now, let's look at two cases. One's called an overdetermined system, where you have a tall and skinny matrix. The other one is called the underdetermined system. That's a fat matrix. For different matrices, you have different solutions. If it is an overdetermined matrix, then the solution is A transpose A inverse A transpose Y. So that's the first equation. If it is an underdetermined system, it's not a full, it's a fat matrix and a short matrix, then you will get you will shuffle the transpose and also the inverse. They're two different things. All right? Okay. So now if A is an underdetermined system, then you can show that there exists a non-trivial null space. Now, what is null space? Previously, we defined the notion of range space, which is the set that contains all the possible linear combinations of the columns. Now, if you have an underdetermined system, you have all these columns, then you have some redundant columns. They're guaranteed to be dependent on the previous k columns, right? So I draw them in two different colors. The blue colors, they are the independent columns, but then you have a set of orange columns. All these orange columns, they will form a space. It's called a null space. And in this null space, there's a very interesting property where if you take this A matrix multiplied with some theta, it will give you 0. And so the null space will contain all the possible thetas such that A theta is 0. Any fat matrix will have this property. Tall matrices, yes and no, depending on whether the columns stay independent or not. Okay? So if you have a null space, then you'll run into some issue, which is that you will find a set of thetas such that A theta is 0. What does it mean? Well, it means that if theta hat is a solution, then theta hat plus theta 0 is also a solution. Why? Well, it's because that if you look at theta hat plus theta 0, and then you apply the A, all right, and then you put the bracket here, you ask, can I find it to be a y? Well, you will get y, and you will get 0. Okay, and so as long as a theta hat is a solution, you add theta hat with a theta 0, you will get the same y. So I give you one y, you will be able to find infinitely many possible thetas, which contains theta hat plus all these theta zeros. They will give you the same solution. Okay? So this is an underdetermined system, and this is not so nice. So what we can do is the following. Okay? So since you have infinitely many solutions, then we ask, which one should we pick? Okay? So if A is a fat matrix and it has all the full column rank, by the way, the rank is defined as the number of independent columns in a matrix. Okay? And by independence, I mean that you form a linear combination. If you set it to 0, then all the linear combination weights has to be 0 because they're independent. Okay? So that's just the definition of independence and also rank. So assume that A is a fat matrix and it has full rank. Then of course, according to the null space definition, you will have infinitely many solutions that can make this A theta equals to y. Or if you go back to this thing here, if I have y here, I can find a theta hat, but any theta hat plus this theta 0 will give you the same y. Okay? So you have infinitely many solutions. So we want to pick one that is unique. Then which one is it? Well, then you need to solve an additional optimization problem, which is that you want to pick the one with the minimum norm. Why minimum norm? Because that will give you a unique solution. If you don't pick the minimum norm, you will still run into the trouble of having multiple solutions. So if you solve this problem, then you get a thing called the minimum norm solution. Okay, so some remark in the textbook. If you read the textbook, linear regression is often referred to least squares. Okay, if you read the signal processing textbooks, it's called the least squares. And then there is a thing called the minimum norm least squares. And where does this minimum norm come from? It comes from the fact that if you have a fat matrix, then you have a non-trivial null space. That means you have infinitely many thetas that can all make that system of the equation to be satisfied. And among all these infinitely many choices of solutions, you pick the one that has the minimum norm. That's why it is called the minimum norm least square solution. Is that clear? Okay, if you ever come across these terms, it means that. So pictorially, what I mean is the following. You have so you can look at this diagram here. Okay, so you have a space that contains all the green arrows. These are the basis vectors. They are the column vectors of the A matrix. And any vector that lives in that space can be a y. Okay, so if you have a fat matrix, and then you have a non-trivial null space, you are guaranteed that your y will live on that space. Why? Well, it's because the following thing. You have, okay, it's because whenever you have a y there that is not living in your null space, you can always create some null vectors so that it will live on your space. Okay? Or in other words, you can always find a solution theta hat to make A theta equals to y exactly. Okay, so that's the problem of the fat matrix. And so since y lives on that space, and we know that there are multiple thetas that can make that to happen, so there's a set of all the thetas. And among the set of thetas, you want to choose one that has the smallest norm. So then you can get a unique solution. So that is the picture behind a fat matrix case. Is it clear? All right. So now let's move on to something even more difficult. Okay, so now we have gone through the column matrix, or the tall matrix, which is full rank, and so you have a very simple solution. And then we talk about the fat matrix, where you have a null space you need to deal with. So now that will be the third case. It will be the most complicated case, where you have columns that are dependent in your matrix. Now, why that will be the case? It happens all the time in your real data sets. You measure someone's GRE score, and then you also measure someone's TOEFL speaking score, and then you measure someone's IELTS speaking scores, and then you're just looking at the English score. Okay, and if you get one high, typically you get highs in the two other tests. Okay, and then you can create some kind of dependency between the columns. So if the dependency happens, then you will have a set of independent columns, and then you have a few columns that are dependent. That will create the situation that I'm showing you on the left, where that can even happen when you have a tall matrix. And so if that happens, what you should do is the following thing. There are two approaches. Approach number one is called the regularization, which has something to do with your loss function, which we will talk about next time. That's approach number one. Approach number two is called the pseudo-inverse. What we do is to do a thing called the singular value decomposition, a thing that you are encouraged to look into a tutorial or not. You want to look into some textbooks. Singular value decomposition of a matrix. So what it does is that you give me a matrix. I'm going to decompose it into three matrices, U, S, and V transpose. The U matrices, they have a dimension of n by n, and then they have a property that when you take the transpose of U times the U, you will get an identity matrix. How about the V matrix? It's a D by D matrix, a smaller matrix. You also have this orthogonality property. And then there is a diagonal matrix. You have an S. S itself is a rectangle matrix. It's like what I'm drawing you here. But then there is a diagonal block. Okay? In this block, you have a bunch of values, S1 to SR, and then they will all be zeros. Okay? Now, if all the columns of this A matrix, they are independent, then you won't get any zeros in your diagonal block. But since they are dependent columns, you will get the zeros in your diagonal block. So if you do the singular value decomposition on your A matrix, decompose it, and then you write it in terms of this, then you can see a very interesting structure. Okay? First of all, your U matrix, you will still get all these columns, but then there will be a part that you don't really care. Why don't you care? Because in the S matrix, the S matrix, you have some entries at the bottom. Okay, they're here because you want to match the size of all these matrices, so you can ignore them. And then you also have the blue and the orange columns. Okay, so they represent the columns that are really the basis vectors for the A matrix. Now I draw them blue and orange. If you go to the diagonal block, you can also see the similar structure where you have non-zeros and then the zeros. Okay? So that would be the structure of your singular value decomposition matrix. So if you have a fat matrix and they are rank deficient, meaning that you have more, you have a non-trivial null space even in your column, in your tall matrix, then what you would do is to take the inverse of the non-zero parts of your diagonal matrix. Okay, so if you go to the equation there, you can see that I put a 1 over S1 and then 1 over SR and so on, and then a bunch of zeros. For the zeros, if you take 1 over that, you get infinity, and that's why you get things blow up. Okay, and so this is called a pseudo inverse. It's not the full inverse, it's just the partial inverse. It's called a pseudo inverse because you take the inverse of the non-zero part of your singular value decomposition. Okay, if you do that, you can solve the rank diffusion problem, and then you will get a solution that will be the best fit for your linear regression problem. Okay, same principle applies to the fat matrix. The fat matrix will be exactly the same thing. However, you want to have a different U matrix and different V matrix. That's the only difference. Okay. Okay. So here is the reading list for today's lecture. It is a very quick tutorial. Goes through the typical notions of linear regression, and I would encourage you to take a look at some of the classic textbooks on linear algebra, and then a couple chapters in the textbooks that you want to take a look, as well as a very well-written tutorial by Stanford CS229. You're also welcome to look at the tutorial of our own course. Okay? There will be an appendix in this set of slides, which will show you how do we solve the minimum norm problem. So you're also encouraged to take a look of solving this constraint minimization problem using Lagrangians. Okay? And then we'll resume our class on Friday.